Okay, thank you. So today I would like to talk about therapeutic nuclear magnetic resonance. So therapeutic nuclear magnetic resonance is a form of nuclear magnetic resonance, but it is low dose. So we have here a range of 400 microtesla. It's not that easy. I try. Okay, good. 400 microtesla, it is the sweep field, and you see it produces a homogeneous field. And perpendicular to the sweep field, we have the radio frequency that goes up to 17.8 kilohertz. And you see it's low dosed, it produces proton resonances, but actually it does not produce a picture as an MRI from the clinic. And this device was actually built by medtech companies 30 years ago for the treatment of wound healing, for regeneration, osteoarthritis, and osteoporosis. 30 years ago, they just built this device and they did not know what happened in the cell. But actually, they expanded and they did not find negative effects, but they just go on. And therefore, some years ago, Margit, who is the chair today, started a cooperation with this company to find out what happens in the cell. And I would like to start now with the chronobiological effects. And therefore, I would like to refer to the talks of Travis and also from Alex, because they told you already that cryptochrome has not only a function of magnetosensitivity, it is also important for the circadian clock. We have a circadian clock in every cell of our human body. And cryptochrome is one of the 4 main hallmark proteins. And to maintain this clock, it has to bind period 2. Period 2 is also very important for the immune function, and therefore we decided to track its promoter region. Promoter region is like a starting point of a gene, and when it's active, we can track it with a luminescent signal. So here in the pictures on the right side with the sun, okay, for you it's left, I'm sorry, on the left side, we treated the cells for 6 hours with tNMR in the morning. And you see that the oscillation in blue is even bigger, so the amplitude is raised. And when you compare it to the nighttime treatment on the right, you see that the whole oscillation is lower. That means that the promoter activity drops dramatically. And this is because of the redox status of the cells, because the cells are during daytime more oxidized and during nighttime more reduced. So it really does matter when you treat your cells. So then we also looked at seahorse experiments. So we wanted to track the metabolism in real time. And I'm sure that you will get also other seahorse data from Reese tomorrow at this talk. So you maybe have also heard a lot about that. Seahorse is a technology where you can track in real time how the mitochondria breathe. And you see that on the right side, left again, on the left side, the OCR levels. And the red curve marks here cells that were treated for 6 hours with hypoxia. So they have no oxygen or kind of no oxygen. It was only 1%. And then they have oxygen available again. That means they breathe like crazy. And that's what we see with this increased curve. And then the blue line marks the cells that had hypoxia together with tNMR. And you see they don't have to breathe that much. So the curve is way lower. And on the right side, the ECAR levels, the extracellular acidification rate, they mark cells that, like ECAR is like a translation for glycolysis, so sugar metabolism. And in red again, you see, of course, they do a lot of glycolysis. And in blue, you see the cells combined tNMR with hypoxia. They have a lower ECAR level. And this phenotype was visible also when we tracked the metabolism over time. So these are steady state levels, and you see here glucose, lactate, intracellularly and extracellularly. And cells that have a high sugar metabolism, they have low glucose level and they have high lactate levels, as you see here with the red dots compared to the normal control groups in black. So low glucose levels, high lactate. But when you look now at the NMR, you see that the glucose levels are higher. They are more in the control group. And you see that they have also not such high lactate levels. So we also found effects in the ROS levels of the mitochondria. You see here on the left side in blue, tNMR and hypoxia control group. And in red, you see just control groups, and you see that the superoxide increased in the mitochondria. And also you see difference in H2O2, and these two states were chronologically uncoupled. So all of these effects were interesting for us. I just showed you some few effects. We found more, but actually we were not sure, was this really because of tNMR, or was this just some kind of off resonance effects of the sweep field or of the radio frequency? And therefore, we redid all of the most important experiments with the different constellations of only sweep field, only radio frequency, or tNMR altogether. And you see from first sight, all of the three things, they do something different. So let's start with the sweep field. You see this homogeneous field, it has alteration in ROS. So here we have a ROS redistribution. We have lower H2O2 levels in the mitochondria, and we have higher extracellular ROS. And this is something we often find in weak electromagnetic field effects. And what's interesting here is that the cells have a higher spare respiratory capacity. And that means that the mitochondria still have a capacity to increase the respiration if they need more energy. When you look now to the radio frequency effects, you see no ROS alterations. So this time the effects were more on the metabolism, and we have here a metabolically restrained phenotype. And this is, you can see it first of all with the high glucose levels in red here. You see tNMR is light blue, the radio frequency is red here, and you see that they have a high glucose levels. They also have then downstream high pyruvate levels, but then we find no high lactate levels, and this is visible also for the NAD plus, the NADH ratio. Usually the downstream of glucose is pyruvate and then lactate. And then if you don't have it here, so if you don't have high lactate levels, you would expect that the mitochondria increase the oxidative phosphorylation, but we have no capacity left to do that because we have this spare respiratory capacity being low. That means the whole metabolism here is restrained. When we go now to tNMR, we have the spare respiratory capacity back again, so it's again increased. They have again some capacity in reserve. And you see that we have higher lactate levels extracellularly. And this is interesting because whenever you want to shuttle lactate out of the cells, you need protons because most of the lactate export is done via the monocarboxylate transporter, and it needs an efficient proton coupling. And then we also found mitochondrial superoxide of being high, and we found high NADP plus NADPH ratio. And usually most of the superoxide in the mitochondria is produced by the respiratory chain over the electron leakage. And due to quantum biology and some papers that were showing or they were pointing out to NOx, we were curious if some of the superoxide may also produce by that. Because when you look at this is the NADPH oxidase enzyme. If you look at that, you see that NADPH is bound to FAD, which we know is magnetically sensitive. And via an electron transfer, we can produce superoxide. And then we have high NADP plus, and that could explain our effects as well. So we decided to knock out or just to block the NOx enzyme. But then we found even higher superoxide levels. That means NOx, in our case, does not play the role of producing more superoxide. And to conclude all of that, we can say that sweep field, radio frequency, and tNMR They're all doing distinct redox and metabolic states. Sweep-field, as you may remember, is altering ROS levels. Radio frequency goes on the metabolism, and tNMR was the only one of affecting both of them. Additionally, I would like to say that tNMR could be an interesting model to study how proton-linked redox changes could modulate the radical pair spin dynamics. And this is exactly because I would like to show you or point out again the work of Ilya Solovyov, because he said that the magnetic sensitivity of a radical pair depends on its local environment. So lifetime plays a role, distance plays a role, but also the local spin environment. And with this, I would also like to point out Bethany, because she did a poster here and she was not working with us. So she had an idea and she has very interesting ideas about proton and electron couplings. So with that, I would like to say we are open for your thoughts, especially physicists, because we are coming from the biological side. And I would like to thank our chair, Margit, who is my PI, because it's very a lot of fun to work with her and think with her. And also our group, Andreas Kodula, who started a PhD or starts it right now. May some of you have met her. And then also Justin and Adriana and our color partners abroad. So the Finnish group, Thomas and Elitza, and also Hadi. Thank you a lot for your attention.